Just confirm you can see my screen.
Yeah.
Awesome stuff. So I'm gonna switch my face off and just go through this. So now, yes, I'm happy that you guys joined. So for your sake, I'm going to just quickly go through SIMTEQ and then I'll hand over to Max for the main content of the session. So for those of you that doesn't know SIMTEQ, we are a South African company that specializes in CAE and simulation technology. We are engineers that focuses on problem solving with the help of engineering knowledge and simulation technology. And ultimately, our focus is our customers, or said in a better way, the success of our customers is our success. And we always help our users to optimize the technology in such a way that we can optimize engineering resources to its best effect, and also gain insight into engineering knowledge, engineering problems, and increase innovation. I'm not going to go through the introduction of our team. I think we've done this a few times in the past with our previous sessions this year. And yes, this will be our last session for our Lunch and Learn series of 2025. We still need to consider what we're going to do for next year. But if you have missed our sessions, it's all on our YouTube page where you can find all the recordings of it. We try to cover the broad scope of what we have available in MEC1 for our customers. Like I say, the original session for today was supposed to be on MEC COSIM. However, our local expert on the topic, Gerrit Visser, is tied up in training this week. So our best friend, or we're not allowed to have best friends at Hexagon, but our best friend, Maxime, has agreed to stand in for him, and we will focus the session on electronics cooling, which will be covered by the Cradle CFD product. I don't have any other slides that I want to cover, except that, Cradle CFD is one of the most, let's not be biased on this one, but it's a very powerful CFD product. Everything from external airflow, from spacecraft to what we see can be applied to city blocks, as also the smaller scale products like electronics equipment, which it is very powerful for. I can't explain it as good as Maxime, so Max, if I can give you the honor to proceed with the session.
Sorry, Zach, can you confirm? Can you see my screen?
Yeah,
okay, sorry.
I can hear you and I can see your screen.
Perfect. I was talking in the wind with a mute mic, so. So
that
hello,
is
everyone.
To the best of us.
So for the one who don't have the pleasure to know me, so I'm a French guy, so very interested about rugby topic this weekend. Beyond that, so I'm a pre-sales engineer for the CFD tools that we have within the MSC or Hexagon portfolio. I've been pushing this solution for the last 10 years, so I think that now I can have a global idea about the perimeter of our solution. And today, so we wanted, as I mentioned, we wanted to focus the session about the electronics cooling. So you know electronics, it's surrounding all of us everywhere. So you have it in your car, in your nearly toaster machine, in your TV, in your laptop, so everywhere. And one of the crucial points when you want an electronic device to work is to manage its temperature. So that's why when we talk about electronics, we always talk about CFD and the way to manage and to dissipate this heat. So during this presentation, I first want to make a quick focus about why should you choose us about managing thermal management for your electronic device. In short, I promise. And then I will show you some features that we have specifically for this industry, for specific topics. After that, I will show you one example that I think is meaningful about what we can bring in terms of simulation capabilities. And then I will finish with many other examples, depending on the time that is left for us. One of my big defaults is that I speak a lot. So I hope you will stay with me, but let's go for this presentation. So why us? I don't know if you have already heard about Cradle CFD softwares, maybe not. So since we are here with SIMTEQ, you must have guessed that it's within the MSC portfolio. Actually, that's the CFD simulation tool that MSC acquired nearly 10 years ago now. And why it would be interesting for you to consider our solution about electronics cooling and electronic thermal management. Cradle CFD, you can see it as a big toolbox. So I'm not even talking about MSC1 tokens that gives you the ability to use any software within the portfolio, but even if you have a Cradle CFD license, you can see it as a toolbox, because in CFD, that's a very wide topic. You can speak about flow, external aerodynamism for Formula 1, for example, this weekend as well. You can consider as well the heat exchange. When we are talking about thermal management in electronics, of course, thermal is of interest. And for example, here about this heat transfer, you can consider conduction, convection. It can be forced convection with a fan, can be natural convection. You can consider radiation as well, solar radiation. I have experienced a few years ago the sun in South Africa, so definitely you should be able to tell the software that you are in Pretoria or in Cape Town or in Paris. That's not the same amount of sun to apply, so we can also do it. And we also have a dedicated tool for PCB, for electronic boards, at a very early stage of the development process. I will show you that in a minute. But consider our solution as a global toolbox for your needs in electronic cooling. Another point, so maybe you won't see it on my face, but our solution is Japanese. And when I say Japanese, it's not popping up of a magic box a few years ago. This solution, Cradle CFD, it has been first released in 1984. Very good year. And our software is designed not in the way that we want to add features, to add features, to add features. We want to bring you a solution. If I put myself in your shoes for a minute, what is the end of your day? When you are facing Coolix electronics problematic, you are aiming for this stage. You are looking for results. You are looking for results to work on and to interpret, to take decision. You are not looking to get a mesh. A mesh is a good way to get a result, but that's not the end of the day. That's why our software is designed in the way that from the CAD geometry to the results, we want this to be as fast and as smooth as possible for a user. We are talking about CFD, we are talking about simulation, and you know that's always the same story, almost. With simulation, the pain point is to get from the CAD to the mesh. If I tell you, okay, we get an assembly of few hundred parts, if you have to run a simulation on that, you will sweat, because you know 100 parts, you need to make sure that every part is in contact. No intersection, no small gap. If you have bolt, nuts, these kind of things, you need to remove them to simplify your geometry. You will waste time to make approximation, so definitely not a good deal. With our solution, we can make you the promise that from the CAD to the result, it will be very fast. And actually, that's always a trend that we observe on customers or prospects that are not currently using our tool at the beginning. When we ask them, how long does it take from you from the CAD to the result? Either if the answer is 1 day, 1 week, 1 month, then we ask them, how long does it take for you to look at the CAD and to get a mesh? And it's more than the half of this amount of time. And that's silly again, because your value is on interpretation of results. on decision that you can take out of it. Your value is not in CAD simplification or model preparation for a mesh. So that's the promise we can give you. With our solution, you will drastically reduce the preparation time. I will show you also some example of that. And once you get your results, okay, so what? You know maybe you know the joke. CFD also stands for color for directors. Yes, you can plot beautiful images. You can bring some CAD. You can go up to photorealistic rendering, virtual reality. No problem. We can entertain as well. But we also know that the end of the day for you, it's not just to get the plot. Then you get the plot and then you have to interpret them to make decision. But it's open for interpretation. It requires expertise. If you are a newbie, maybe you will be lost. You get your result. Okay, it's too hot. And so what? You are on your own. With our solution, not only we bring you the beautiful plot, but we also give you this analytical view of the results. When you know where to look at or when you don't know where to look at, you can look at your assembly. You can get a kind of traffic jam map of the heat inside your system. You can see if you have bottlenecks, if the heat is behaving as you expect. But you can also look into detail and to check the heat balance, to know, for example, if you have a part that is too hot, where the heat is going from, and then where the heat will going to. I have an example in mind, a customer that has some water tightness constraint on the electronic system. So of course, to evacuate the heat, they design the housing in aluminium, more conductive. So okay, that's a good idea. And then they design some fins on the external shape of the box. Okay, it will act as a dissipator. That's a good, again, that's a good idea. But thanks to this kind of results, they have been able to notice that more than the half of the heat evacuated from the system was through radiation, not convection. With this level of insight here, they have been able to say, okay, let's remove the fin, and then we will save some money for the anodization of the surface, because radiation is the best way to evacuate heat. So this you can get with this kind of results, not just color plots. So I hope now I have raised your interest. Okay, this guy could be interesting in terms of electronic coding. Now I will show you some features that we have dedicated for this specific industry. The first of them, it's called PICLS. I'm sorry for the name. I'm sure that's a very smart acronym, but in terms of naming, maybe that's not the most appealing. What is PICLS? Here you can see directly a screenshot of this tool. So as I said, it's focusing on the electronic board. And the good point is that you can do it in live, in meeting. Maybe you have a project review, you can use this tool directly in the meeting. This screen capture, it's in live. So it means that at the beginning, you can start from scratch, just drafting your PCB or your electronic boards, or you can directly import ECAD file, IDF file. So you load your electronic boards, meaning components, wiring in the different layers of your component of your board. Here, it can be two layers conductive, can be up to 16 conductive layers. You just describe what are the thickness of the copper, what are the materials, and then you can give some information regarding the key target component of your board. And as you can see here, it's in live. It's not mounted then on Adobe Premiere or whatever. It's in live. You get result in second. So for example, here you can see the temperature distribution on the board. And then what if? What if I thicken one of the conductive layer? What if I just translate a bit a component? And then you just re-click on the results, and then you get your feedback directly. As I said, you can use it in live during a meeting. So the point, of course, it's not to go up to 0.1 degree precision. Actually, you can be surprised sometimes because we can also get some very nice accuracy. But the point is to get a rough idea about what will be the thermal behavior of my board. Because at this stage, you are very early in the process. At this stage, you are very focusing on the electronic board. But if you are not fixing and anticipating thermal issues of your board very early in the process, then it will be very painful and potentially very costly to fix this kind of problematics. So the earlier you consider thermal problematics in the process, the better it is for your design. So again, here with that, so our sales guys are very disappointed because this tool is so simple that they cannot sell a training on that. Actually, if you just take 20 minutes for a remote session, then you will be trained on this solution. And actually, I always tell my sales colleague, even you could use them. So if a sales guy can use it, no offense, Zach, but I know you are half technical. But if a sales guy can use it, everyone can use it. So that's what we have at the early stage of the process on the board itself. But what if I want to consider the system as a whole? So yes, you can consider just the PCB at first, but then maybe you want to consider fans. Maybe you want to consider the housing. Then you will get to mesh it, because in this early solution here on the board itself, we are not talking about mesh. So if you want to consider a global picture of your system, then you will have to consider a real simulation tool. By real, I mean you have to prepare the simulation, apply material, boundary condition, these kind of things. Then you will get your fancy plots or your insightful plots as well. You can make design change and compare different configuration. But let me show you what we have when you want to move further in the process. So far, we have been interested about the electronic boards themselves. So we are using this funny name PICLS solution. But if we want to consider the mechanical CAD surrounding the electronic board, that's the tricky point of electronics. That's the meeting of two different worlds: mechanical CAD, electronic CAD. And to make a good simulation of your system, you need to merge both of them into a single simulation model. That's what we can do here. As I told you, this software has been first released 40 years ago now in Japan. And the good point about electronics is that Japanese guys, they know a little bit about electronics. So we have the full legacy of 40 years of experience with the biggest name in the industry. If we are talking about Sony, if we are talking about Panasonic, these kind of guys, they are using our software. So here, regarding ECAD, we can use all standard file formats for information regarding a board. If I take the older one, Gerber files, but that's not very trendy. It's very old-fashioned format. We can use as well ODB++. We can use IPC file format. That's something that is maybe 5 years old now. It's a kind of neutral file. It's the equivalent of step file for electronics. So we can use all these kind of formats to take all the information about the board and the component into the simulation model. But on top of that, we can also add the CAD, the mechanical CAD that you have designed for your system. Either if you are using SolidWorks, CATIA, Inventor, NX or whatever, but also neutral files, step files, parasolid files. So we merge all of them into one simulation model. And then from there, we are able to consider specific information relevant for our simulation. If we are talking about the PCB itself, tricky thing here to catch a realistic thermal behavior of an electronic board, you need to consider that across the thickness, it will be quite resistive in terms of temperature. But in the plane, it can be quite conductive because you have these wires made of copper. So of course, it's conductive. If you cannot catch this thermal behavior, this anisotropic thermal behavior of a board, you cannot expect accuracy in your simulation. But depending on what you have, because are you early in the process? Are you mostly at the end with a frozen design? Depending on what you have, you can feed the software to get these anisotropic performances. If you have nothing or just maybe a description of your board, you can just specify the software. I know that I have X conductive layers of copper. Their thickness can be 35 microns for one, maybe twice bigger for another one. And then I have some FR4 insulating layers with this thickness and so on. You can just describe the different layers as a software to calculate equivalent properties to be applied on the electronic board. When you have nothing or just a description of the board, it's enough to catch this phenomenon, this thermal behavior. But if you have more information, if the ECAD process has been a little bit further, if you have already the wiring of your conductive layers, you can use either Gerber files, but that's not my preferred one, because it's quite tedious, because you have to position, Gerber, that's just a picture that you put, somehow a layer that you put on your in your system. I prefer ODB++ or IPC because you load them, it will automatically apply by default, but of course you get the control if you want to change, but it will automatically apply copper condition for wiring, insulating properties for the FR4, so that's very straightforward. You import it and your board is almost ready. The only thing you have left to do is to specify what level of accuracy you want to keep in the meshing process. But I will come back to that later. For electronics, okay, we have components. We have specific devices, fan, heat pipes, Peltier device, these kind of things that are some possibilities to manage the thermal behavior of an electronic system. All these devices, if we are talking about component, a fan, and so on, if you want to strictly simulate them, it can be very complex. If you think about a chip, if you want to consider what is inside the chip, you have to look very little detail information. You have to mesh very fine. You can do it. Actually, we have some customers like Thales in France. They are really meshing the detail of each chip with the gold wire and all this kind of details. But what are you interested in? About the chip itself, or more about the global consideration of your system and what will be the macro impact of your chip on the system? If that's more in this second possibility, we have also the ability to provide you here and to represent components with what we call compact thermal model. You have a chip, very complex what is inside. You will just convert it into a 2 or 3 resistance model, a Delphi model, or your own customized thermal model, meaning that your component will be nothing more than one node at the center where the heat will be generated, one node at the bottom that is in contact with the board, one node at the top who is in contact either with the air or maybe with the heatsink. So that's the same principle here for the Delphi model, but maybe with more information, more detailed information. But you get the drift. You have a complex system. We just want to represent it in a very simple way so that we can catch what is the impact of this system on the rest. And that's the same for the fan. If you're a fan manufacturer, of course, you will be interested about meshing in detail, about the different blades and so on. You will be interested in that. And then you will make a transient simulation with the motion of the fan. You can do it. But if you are more designing the electronic system, maybe you will buy the fan to Sadio or whoever provider. And what you are interested in is to get the PQ curve, so the performance curve of your fan, and you just want to catch the behavior of the fan on your system. Same way then for the components. You have a fan, we'll just convert that into a fan model. You can give the PQ curve, then it will calculate automatically what will be the working condition of the fan, but then you get the effect of the fan on the system. You are not looking into the detail of the blade themselves, but you are looking about the impact of the fan on the system. The same for the heat pipes, the same for the Peltier device, these kind of things, okay? So we have modelization for all that makes sense in electronic world. Other possibility, maybe you have used in the past another simulation tool, and you have a full legacy of components, of subsystem that you have represented. Maybe you have your own library, and you don't want to lose all this legacy. Good news is that we are open for XML exchange, meaning that from your previous solution, you can export your subsystem in this format, and then within Cradle, we are able to import them. Okay, so that's a standard format exchange for simulation tool in electronics. So you can also leverage the legacy of your usage for previous tool. We are talking about electronics. More and more, it's always the same story in electronics. You want smaller things with more power, miniaturization. So that's very convenient in your usage of a device. A laptop can be smaller, lighter, so it's very convenient. The bad point is that you have more and more power. And sometimes when you have high power passing through conductive materials, you get what we call the Joule heating. So on a functional perspective, that's not a big deal. But here we are talking about the thermal prism of the consideration. We want to manage the heat. And the bad thing of Joule heating is that this current, this high current passing through a conductive component or material will generate heat. So not only the component will generate heat, but sometimes you can also get some heat produced directly by the current passing through conductive material. So we can also consider these kind of things. Here, just a view of inside an inverter. You have some IGBT modulus, and you have some bus bars, and these bus bars can go very high in temperature just due to the passage here of electric current. So we can consider it as well. Now I want to make a focus on the mesh. As I told you, that's always the tricky and the very touchy point in a simulation process. How to get a mesh. If you have a mesh really easily, that is your day, because you don't, you won't bother yourself with CAD preparation or these kind of things. If I want to show you here this screen capture, so again, that's a live script capture. I didn't took it and mount it on a software just to give you the impression it's fast. Here, it's a model. It's a Raspberry board. Actually, I've just removed here the housing, but actually the housing was part of the simulation. If we have a look at this model, you have bolts with fillets. You have component in detail. We have thermal pads. We have marks. We have intersection. You see these small connectors. So here, this metal folded, metal sheet folded here part, that's a nightmare for a meshing process. If you can imagine, I don't know what you are using today, but if you are imagining to pass this model into your simulation tool, of course, you will have to simplify this geometry. Here, not only it's complex, it's crappy, let's say. You have intersection with the board. If I move a bit further here about the complexity of this CAD model, so it's just few hundred parts, no, just few hundred parts. But you can see all the complexity, all the details are here. You see here square pins in round holes. That's a nightmare on a meshing perspective. But here we are using Cartesian mesh. For Cartesian mesh, what you do, you just specify the global edge length that you are looking for your cells, the level of detail that you want to be kept after meshing process, and you can do it in X, Y, and Z direction of your system. That's why we call it Cartesian mesh. You can make something different in the different direction, or you can use isotropic properties. That's very convenient if you think about the board itself. If you want to consider the wiring, maybe you want to catch very small detail in the thickness to catch every single layer of your board. If your wiring is very detailed, maybe you want as well some very thin accuracy regarding the plane direction. So it's very convenient here. And you can create some sub-blocks, meaning that, for example, for the PCB itself, you will use a set of parameters, and for the rest, you can use other things. But again, here, we are just specifying global edge length, what we want to keep, and that's in live. This meshing, I think this one is something like 14 million cells. It has been done on my laptop. So it's a good laptop, but it's still a laptop. It's been done within 5 seconds. So 100 parts assembly with detail, intersection, and blah, blah, blah. All the crap that you can imagine from a complex CAD file. You just specify 2 parameters, you mesh it within 5 seconds on a laptop, and you are ready to go. So if you remember when I promised you that we will bring you to the result as fast and as smooth as possible, this is why we can be so bold about these promises, because with these meshing techniques, that's really easy. So here in live, we mesh it, and you are ready to go. So the only thing left is to assign materials, but you can do it like a grouped selection. Typically, for this kind of simulation, we would spend something like 20 minutes to set it up. To mesh it, a few seconds, and then to solve it can be 1 hour, 2 hours, depending on the complexity and the kind of phenomenon, physical phenomenon that you want to consider, but it's very straightforward. So I was not lying. Yes, we can mesh anything within seconds. If we are talking, so yeah, maybe I have an example right after, but so that's a Cartesian mesh. You can see here this kind of stairway shaped. But if for a specific reason you want to recut the cell, we also have what we call the cut cell. So here, Sony PlayStation, if you recognize the controller here, instead of using a fine mesh here to represent the thickness of the housing, maybe you want to cut the cells of this housing. Maybe for the joypad it's not necessary, but as you can see here, you can also target what solid parts you want to recut in terms of meshing. And as I told you, we can create also some fancy animation to entertain. So yes, we have photorealistic rendering even on this cut cell meshing stage. This example, an electric cabinet, an assembly made of 5,000 parts. You have a front door with something like, I don't remember if it's 9 or 12, but you have some fans on the front door. We take this model, 5,000 parts, as you can imagine, you have all the wiring, all the bolts, the nuts, and so on. If you are not able to use Cartesian mesh, you will have to rebuild a simplistic model to be able to simulate it. With us, you take it, you import it, you mesh it. Actually, here it took something like 5 minutes to import the assembly within the system. It took less to mesh it. So, and you can see, no cleanup at all. Within 5 hours, we get the first set of results. We are also able to consider humidity. Electronics and water, you know, it doesn't get along very well. So, but I'm not talking about different solution, a different simulation. Maybe one simulation for thermal and then one simulation for humidity. We can consider them as a whole in a single simulation model. Actually, we also have some customers using our softwares to do some IPX ingression characterization of their system. And we can also consider dew condensation. So that's not the animation, but we can consider dew condensation and its impact regarding, for example, the PCB. Because if a PCB catch humidity, it will affect the thermal behavior of it. We are talking about new trends and so on. If we are talking about additive manufacturing, if you consider very complex dissipators, this kind of lattice structure dissipator, we are also able to consider them. Not only we are able to consider them, but if you think about traditional approach, out of n-top solution, you create a very heavy STL to catch this shape, and then it takes hours, if not days, to be able to mesh it and to use it in a simulation perspective. On our side, we have developed a partnership with n-top. We are able to directly use implicit file. That's crazy. This kind of very complex shape and so on, it's few, I don't know if it goes to the megabytes, but few bytes for sure. It's very light file, and you can directly use it and mesh it. One of our customers in Japan, it used to take something like 3 to 4 days to simulate the process with the dissipator. With us, it was shrink to few hours. Just a use case of an inverter here. As I told you, we can go very far in the detail. This inverter, you have some IGBT modulus. In this single IGBT, in that case, they wanted to go on the very sub-level with the different substrate, copper layer of the chip and so on. This system was cooled down thanks to a water jacket that was cut directly in the housing, made of aluminum. And with our solution tool, we have been able to go into that level of detail on the same simulation model. To get, for example, this cross-section of the temperature, depending on thermal pads that you are using, because these IGBT modulus, they go very high in temperature. They are just put on the top of the water jacket, and we want to control the temperature. Depending on the performance of the thermal pad, you can see what is the temperature that you can force your component to remain at. With a low performance thermal pad, this temperature will go something like 130 degrees. If you put more mode in the thermal pad, you can see that the shift is something like 20 degrees. Is it worth or not? That's your call. But again, we provide you the result and then your call for the decision. So with this, we have been able to calculate the thermal behavior of the electronic system, even if a water jacket is involved. I just wanted to show you briefly, because I'm just looking at the time. Yeah, I've been quite talkative, but just few examples. Here, this one, it's a company that designs some, so it's a French company, this one, designing some very complex system able to mix or to handle the video flux on big screen. So for example, here, mega screen on Times Square. If you go to a very big show of Taylor Swift or anything in Vegas, for example, you can see all these big screen on the background. Their devices are used to manage the video flux here used in this. Their system here, I think it's something like 28 different electronic boards inside the system. So quite heavy baby. But thanks to Cartesian mesh, it was not a problem for them to use it. So a monster assembly as well, more than 5,000 parts. They took it, they mesh it, and within a few days, they have been able to simulate that. And on the top of that, our post-processing capabilities, I told you, we are able to entertain as well with virtual reality, augmented reality, these kind of things. They knew that their main competitor, their pain was on the thermal management. And if you remember, I told you about Vegas screen. If it's outdoor concert or shows, of course, it can be quite constrained in terms of thermal environment. They knew that their competitor was struggling with thermal management. So you know what they did? Once they fixed their issues with the simulation tool, they produce a 8K resolution animation showing the thermal management of their system, just to demonstrate that, yes, they are using simulation tool to make their simulation, and they are doing better than their competitors. And with 8K resolution video, of course, they are able to display that on very big screen. So you can guess what delight it should have been to show their master management in big screen in front of their competitors. Another example, different scale. We have been talking about very complex model. Here on the other side of the range, we have some customers designing some chips. Here in that case, Nexperia. They are designing at the very low scale here, but they are using the same simulation tool, the one that I've been describing. They are using it here for their chip. They are using PICLS, but also scSTREAM. So the very simple one on the board level, this one, but also the Cartesian solution that I've been describing later on. So they are very happy with this solution, because not only they can do some very quick simulation, very rough simulation on a very big level, on the board level, but they can also go into detail on their chip, producing something like dozens of million cells just on the chip to go into the level of detail. Maybe my last example here. So I don't know for you, but I'm a big fan of Formula One. You know these guys, Red Bull. They are using 3D scan to check if the different parts of the car are aligned with the virtual prototype that they have been working on for the development. These scanners, they are designed by Leica Geosystems, and previously they were using another simulation tool. It took them from 2 to 3 weeks from the moment they received the CAD to get the results. By adopting our solution, they have been able to reduce it to 2 to 3 days. So you fall by 7 the time spent on simulation. You can imagine the gain in terms of productivity. Instead of waiting weeks, the day after you get your results. That's very high-level acceleration for the design process. So here, no magic. It's just that instead of wasting their hours or their days on CAD preparation, they can just drag and drop it and mesh it. As simple as that. So I will just pass very briefly to the conclusion of this. In case you fell asleep, wake up. Now, you didn't miss anything, because if you just need to remember why using our tool, you will save huge amount of time on pre-processing with the meshing process again, this kind of complexity, few hundred parts, you just take it, you specify global edge length, detail of detail you want to be kept after meshing process, you mesh it, and within few seconds, you get your mesh. As simple as that. So you save time on pre-processing, but as well on post-processing. Yes, you get the fancy picture to entertain your sales colleagues or your boss, but you get also very insightful level of detail here. How the heat is behaving inside the system. Do you have bottleneck? If you have bottleneck, how to fix it? Maybe the heat is going in a direction you were not anticipating. So you can see where the heat is going to, and you can see as well what heat transfer is your best ally to remove the heat from a tedious area in your system. Do you want to maximize convection, radiation, conduction? Again, that's your call. But with this, you get the full vision of what we can do. So I hope you get some interesting point here in this presentation. I hope you have been able to think maybe of your own development process. Maybe some bits of this presentation could ring a bell to you. And if you want to try it, of course, get in touch with Zach, and we can discuss about this for your own design process. So thank you very much. I don't know if we have time for question, or if that's the habit for this lunch and learn session, but I think that's all on my side. Thank you very much.
Thank you very much, Max. That was as insightful as ever with all your presentations.
Thank you.
I'm a bit disappointed that you mentioned all your preferences, like Red Bull Racing, the Springboks, in the same preference pool as Taylor Swift.
That's
but
my
I'll leave
professional
it there.
preference. That's my professional preference, because to be honest, I have a crush on Hamilton and Ferrari. So
I'll forgive you. Is there any questions from the listeners that you're more than welcome to ask us or ask Max?
And if not today, you can still bring it up later on.
Of course. Jonathan, maybe anything from your side, since you're on such high on presenting at our student users conference as well.
Unfortunately, nothing from my side. Thank you. Very insightful presentation. So thank you very much for that.
You are very quiet, but if I heard you correctly, there is nothing. It's just insightful from your side.
Thank you.
Okay, Max, I'm not going to leave you hanging. Thank you very much for helping us out.
Thank you for your time, and have a nice weekend.
Awesome. I will be in touch regarding our other conversations, but yeah, I think this is a good intro.
Thank you. Bye.
Thank you, everyone. Bye-bye. Enjoy the weekend.